attending any conference, it's incredibly important to be there. That's kind of the only way to really dedicate your time to be there and kind of be immersed in the whole thing and not distracted by other stuff going on, even if you do get distracted with interesting conversations in the hallway.
All right, folks, thanks for coming. I would say it's almost over, but we have still a full day left. And from when I checked in the schedule, tomorrow looks jam-packed with good sessions as well. So I'm really looking forward to that. But let's rewind a bit to 2019 when I was last time here. I had this slide up, and I said, hey, it's our first time here at the Gaylord Rockies, new venue, same great conference. And I sort of trolled. By the way, if any of you have been here last time, you probably recognize that area, that space there. And I sort of, at the time, I put up this slide in 2019, and I sort of trolled that I have concerns about that train going on the track there, if that would fit on the bridge, because there was like a beam there. So I sort of did the measurements, and I complained to a few people, and then this happened. So feedback really matters, folks. So this applies to this presentation as well, but for all others and all other concerns that you might have, do reach out to folks, speak up. Apparently, speaking up matters. So, getting on to today's topic, regular revisited. Why? I think you've seen this giant pitch already. Sorry, I don't have any band, any music here, but just picture some Beatles background there. So this was in Herb's keynote this morning, of course. We have to think about the classes we write. We write all sorts of different types of classes, whether RAI types of things, utilities, wrappers, callables, all sorts of polymorphic types. We write class generators using class templates, and we write containers, we write value classes. Of course, today I'm going to focus specifically on value classes. But I'm going to mention a few of the others as well. So some are more special than others. I gave this similar talk in the same vein, similar title, 5 years ago at CppCon, regular types and why do I care? And it was fairly popular at the time, and I've been asked to do a reprise or up to date with C++20 and maybe stress some of the points a bit more for folks who missed it. So why revisiting regular types? Because good types are all alike, while every poorly designed type is poorly designed in its own way. The Anna Karenina principle of designing C++ types. Why are we talking about this? We shall see that regular types naturally appear as necessary foundational concepts in programming, and we'll try to investigate some of the requirements that the C++ standard imposes on some of these types, either the ones that we provide that need to interact with the standard library or the language, or how we use what the library actually provides and the built-in types, and how they all fit with algorithms and data structures. Even CPP core guidelines mention the word regular quite a few times. There is one prominent clause there, make concrete types regular. And it says, regular types are easier to understand and reason about than types that are not regular. Irregularities require extra effort to understand and use. C++ built-in types are regular, so are the standard library classes, such as string, vector, map, and so on. And concrete classes without assignment or equality can be defined, and we do regularly, but that should be something that should be taken with care and should not be the norm. And I'm going to show rationale why that is. And we have another one, require template arguments be at least semi-regular. Don't worry, I'm going to clarify what all these things really mean. And the reason here given by CPP core guidelines is readability, preventing surprises and weird errors. So getting back, the talk is not just about regular types, although the title. It's a moment to reflect back on STL and its design principles, as best described in the seminal Stepanov paper from, yes, 25 years ago. I cannot believe it's been 25 years. So we're going to talk about values, objects, concepts, ordering relations, requirements, equality, whole part semantics, lifetimes, and we already mentioned core guidelines, of course. And it's going to span more standard revisions. But I want to get started with, it's actually a two-part series. It's an older presentation by Titus Winters, Modern C++ API Design. It has two parts. One focuses on type properties and what properties can we use to describe types. And another one, the other part focuses on type families, combinations of type properties that are useful in good type design. I highly recommend that you watch this two-part series. I think it's from CppCon 2018, if I remember correctly. Links are in the slides. By the way, slides are full of links and references to other papers and recordings and articles. I'm going to share the slides right after the talks, so feel free to browse at leisure. But let's start at the beginning. And the beginning would be 2000 BC here. And my first recommendation, I see Roy here in the audience. He already had quite a few Stepanov references. I'm going to add more. I found this tremendously enjoyable. The 4 algorithmic journeys, if you Google for it, there are actually 3. As all software projects, it got revised during implementation. So it's a fantastic series of lectures by Stepanov. It spans 32 hours. So you can binge watch it. Trust me, it's beyond any Netflix special that you might want to consume. At least it's my kind of thing. If you want the written version of that, you might have noticed that I have some props here on the stage. One of them is this book, From Mathematics to Generic Programming. Who owns it or has read it? See a few hands, more should be up. So this would be the written version of those lecture series. And it spans 4,000 years of mathematics and evolving an algorithm and applications and historical tidbits that are very enjoyable, and abstractions and how mathematics and different branches of mathematics developed over time to make sense of these things. So let's start. We need to, before we get into this, we need to establish a sort of common vocabulary, because many of the terms that we usually hear and reuse all the time, sometimes they tend to get different meanings. So I want to set a bit the context for the definitions I'm going to use, the words. So taking right out of the other prop thing I have here, people recognize this yellow book? Yeah? OK. More on that later. So that's the EOP. So a datum is a finite sequence of zeros and ones. And we can represent anything with this. A value type, and this here I need to be very specific in how we define, and these are not my definitions, these are the definitions from Elements of Programming Force. A value type is a correspondence between a species, abstract or concrete, and a set of datums, which are the representational format. Value is the datum together with its interpretation. So we need to give it a semantic, an interpretation to that series of bits. For example, an integer represented in 32-bit 2's complement big endian. That's an interpretation we give those bits. A value cannot change. A value is 5, right? We don't change values. And we sometimes overload this word when we talk about code. Value type and equality. And I'm going to spend quite a bit of time on equality today. But to get started, if a value is uniquely represented, equality implies representational equality. We need to set that as a bare... Somebody doesn't agree with me. If a value type is not ambiguous, representational equality implies equality. Again, I'm going to let this sink in a bit. And when we talk about objects, no, I'm not talking about OOP. So object in the strictest sense of how we represent stuff in computers. An object is a representation of a concrete entity as a value in computer memory, given its address and its span, its length. So an object has a state that is a value of the same value type. And the state of an object can change, of course. That's why we use computers, and that's why we have memory, right? Type is a set of values with the same interpretation function and operation on those values. And a concept is a collection of similar types. And all these concepts I mentioned earlier are from the yellow book on the floor there, Elements of Programming. By the way, I don't know if you can still purchase it. I don't know if it's still in print, but definitely it's available in electronic format at that link. You can download it for free. Some of the chapters in the book that overlap with my material today are the ones that are in boldface. Roy shared a bunch of presentations yesterday from Stepanov. I'm going to add more to your curriculum or to your reference slide collection, your watch list, if you will. So this one is a very good one, and not many people know about it, and I keep sharing it so that more folks watch it. Mathematics really does matter. That's the theme of this talk. But you might say, hold on, I've been programming for many years, and I've never needed any math to do it. I'll be just fine, thank you. Why should I bother with all this nonsense? Well, the reason that things just worked for you is that other people have thought long and hard about the details of the type system and about the libraries that you're using, such that it feels natural and intuitive to you, and it makes you avoid common pitfalls and mistakes. But it's not perfect. Not all types are perfect, even the ones we standardize. So 4,000 years of mathematics leads up to this paper, which I mentioned earlier again. And this paper introduced the concept of generic programming and says that it depends on decomposition of programs into components which may be developed separately and combined arbitrarily, subject to well-defined interfaces. Among the interfaces of interest, the most pervasively and unconsciously used are fundamental operators common to all C++ built-in types, as extended to user-defined types, such as copy constructors, assignment, and equality. And this is going to be what I'm going to show with examples and some of the rationale behind it. Stepanov goes further to say we must investigate the relations which must hold among these operations to preserve consistency with their semantics for the built-in types and the types in the standard library, and with the expectations of the programmers. So we need to have consistency with built-in types, we must match intuition of the programmer, and we must be in line with the mathematical tradition and mathematical education that we get in school. If we learn something in school about comparison or about equality, we must not be surprised if we define it to be different when we program computers. So, in other words, we want a foundation powerful enough to support any sophisticated programming tasks, but simple and intuitive to reason about. And simplicity is a good goal. I claim this all the time. I really hate it when C++ programmers like to brag about being able to reason about some complicated, sophisticated language construct and being proud as if they've discovered some, I don't know, physical law or something. We don't need to be proud of understanding complicated things. We need to simplify things. So another resource, if you find the original 98 Stepanov paper, I don't know, maybe too difficult to digest, maybe you're not ready to grasp all the concepts, I'm hoping I'm going to help in that regard. An easy gateway towards that would be this article by Titus Winters from 5 years ago on regular types. I think it's a good synthesis of the Stepanov paper, as well as an up-to-date analysis on some of the newer additions to the language. So I strongly encourage you to start with this one and maybe work your way to the original Stepanov paper. So it includes things like string view span, and of course, discussions on type regularity. All right. So let's go back to the roots. If you've been in Roy's ranges presentation, you've seen already snippets from this recording. Highly recommend that you watch it. It explains some of the design principles behind STL, things that hold up to this date, and things that I believe all C++ programmers should be aware of. And I'm going to try to summarize highlights from that presentation. Fundamental principles. Systematically identifying and organizing useful algorithms and data structures. That needs to be an ongoing task, not just for library developers, for us as well. Finding the most general representation of algorithms. Using as much as possible whole part value semantic for data structures. And we have newer language experiments like Hilo, which make this center stage for the design and principles of using a programming language. Using abstractions of address iterators as interface between algorithms and data structures so that we have a nice decoupling and we don't implement sort for every other type of data structure. Algorithms are associated with a set of common properties, and a difficult task is identifying these common properties and abstracting them, trying to find a general setting for them. As an example here, operations like, an example comes right from Stepanov, operations like plus, times, min, max are all associative operations. And that means that we can reorder the operands, and that means we can leverage parallelization and reduction when we orchestrate such computation pipelines. And we have algorithms in STL for those operations. All these are natural extensions of years and years of mathematics pursuits. On data structures, and this is going to be relevant for our discussion on regular type design. STL data structures extend the semantic of C structures. This is just legacy. We build on top of it. And that's a good thing that we're inheriting. Two objects should never intersect. They are separate entities. Two objects have separate lifetimes. These should be desirable properties of the types that we're building. It's not always the case, but this is what we should strive towards. Again, on whole part object semantics. Copy the whole copies all its parts. When the whole is destroyed, all the parts are destroyed. Two things are equal when they have the same number of parts, and their corresponding parts are in turns equal. Sounds obvious, but we're very much guilty of not implementing such designs. Again, carrying on from Stepanov's presentation on generic programming and STL and his design principles, some of the drawbacks, it's not all perfect, some of the drawbacks of generic programming, sometimes, rarely, abstraction penalty, implementation in the interface, early binding, horrible error messages, only 99% of the cases, duck typing, and of course, the occasional surprise that some operation will work with existing types, but will fail to work with stuff that we define later down the line. So we need to fully specify the requirements on the algorithm types that we expect to work with our operations. And STL comes with a set of named requirements. A bunch of examples are here on the slide. Named requirements are used in the normative text of the standard to define the expectations of the standard library. And some of these requirements have been formalized in C++20 using concepts. Not all of them, but a good majority of them. If you want to see some examples, here are a bunch of them. We see familiar concepts like equality comparable, ordering relations, of course, regular, semi-regular, and so on. And I'm going to dig into some of these. There are more concepts. For example, in the iterators library, there are more traits and concepts. In the algorithms and ranges libraries. So there are many, many concepts. But they're not the focus of this discussion. So what is a concept anyway? Formal specification of concepts makes it possible to verify that template arguments satisfy the expectations of a template or function during overall resolution and template specialization. Each concept is a predicate, and it's evaluated at compile time, and most importantly, it becomes part of the interface of the template where it's used as a constraint. So what's the practical upside? Sounds like theoretical mumbo jumbo so far. If I'm not building libraries, if I'm not an STL maintainer, why should I care? Well, you are using those things. You are using STL algorithms, you are using those structures, and you are designing and exposing your own vocabulary types across the interfaces and the APIs that you either consume or design for others to consume. So you should care about these concepts. I like to pick on a very simple example here. We all, at some point, need to sort things. Sometimes I do guest lectures at my alma mater, and this is the example I pick and ask students, and they're immediately surprised about the outcome. So what should be the requirements for the compare callable that we're using for the standard sort? Because we're using standard sort and we don't even think about it. We jam a lambda in there or whatever, some function object, and it just works most of the time. But what are the requirements? Well, first it has to be a predicate, and it has to be a binary predicate because we need to compare stuff. And it sort of needs to look like that. We see this in CPP reference. We're used to writing things in this fashion, either as lambda or some sort of callable. But what kind of ordering relationship is needed for the elements of this collection? Those T's in the collection that we're sorting, how should they behave? If they have defined a way of comparing those types, how should that work? If they don't, is the standard synthesized one appropriate for that type we designed? If we're providing a lambda and we're doing an ad hoc predicate, is that predicate good enough for the purpose of sorting those types? And this is the example I usually throw students. I don't know if it's readable enough, the predicate that's right below the picture there. And this is a predicate that is meant to show students that it's very tempting to write such a thing, and usually when I ask them to write it, this is the first thing they write. And of course, it's wrong, because it violates one of the requirements of the compare predicate that sort needs. And the reason is, and it's visible in the picture I hand drew there, is that what we're establishing here between those points, the idea is to compare some 2D points, we're establishing a partial order, because we have, given that predicate that we have chosen below the picture, we have two situations, 2 points, which have undecided ordering. And we say that they're equivalent with regards to that predicate. So partial ordering is not enough to compare and to sort things. We need something a bit stronger. And what we're lacking is transitivity of equivalence. In our example, points P1 and P2, or P2 and P3, P1 and P3 are equivalent. So we need transitivity of equivalence. So we need strict weak ordering. And equivalence just means that when we compare A to B or B to A, either are, both of them are false. So we cannot decide. We say, with relations to this comparator, they're equivalent. So this is what we're lacking. The last line in the table, the transitivity of equivalence, was lacking from that partial ordering predicate that I intentionally chose. So without transitivity of equivalence, the sort algorithm will not work. And if we're not building a strict weak ordering for those types, the operation will not function as expected. And we can see this even in CPP reference if we're browsing. So if we're methodical and using the documentation, there should be no surprises. But people just throw in a lambda there and just pray it works. So if we're replacing that generic comp that I used previously, and we replace it with a familiar glyph, the less than operator, then we get another named requirement from the C++ standard, which is less than comparable. And this, I just repeated the same requirements there. And now the equivalence relation just means that we cannot say A is less than B or that B is less than A. We just cannot decide. And if we move further, in the previous slide I shared, we have one more requirement, and that is equality comparable. And this one is even trickier. And its laws, its requirements, or its definition is that something we learned very early on in school. Like, I think my daughter already learned it in the first years of math. When we learn about equality. Reflexivity, symmetry, transitivity, these are the things we sort of take for granted. Yet, sometimes our types do not. So we need to have an operator equal with standard semantics. If we go back to the concept as defined in the standard as of C++20, equality comparable just lists in a formally checked way the same things I've shown in the table previously. So for types that are both equality comparable and less than comparable, STL makes a very clear distinction between equality and equivalence. And sometimes, although we use it frequently, we even leverage this nuance, we don't pause to actually internalize the significance of the fact that equivalence and equality are not always the same. And there are many legitimate situations where we actually mean to check for equivalence. And we defined operators to check for equivalence of instances rather than true equality. And that's fine in many use cases. And of course, equality is a special case of equivalence. And formally, we say that equality is both an equivalence relation and a partial order. And that just stems from the fact that it satisfies all the rows in those tables that you've seen previously. And there's one more concept that is pretty important in STL, and that is total ordering. And if you remember, maybe you glimpsed at the initial slide where I've shown some examples of C++20 concepts. This was one of the concepts. So total ordering relationship. We say that the comparator function induces a strict total ordering on the equivalence classes determined by the equivalence function that we have. Or we might phrase it that the equivalence relation and its equivalence classes partition the elements of the set that are totally ordered by less than operation. Sounds all very dry and mathematical. How does that help me? So the concept as defined in the C++20 standard looks sort of like this. Again, should be no surprise aside from the boilerplate and the mechanics of defining concepts. Just lists the requirements I had in those tables with the mathematical notation. And total ordering is just another way of stating a mathematical law of the law of excluded middle, where we need to be able to fully order 3 or more elements. If 2 elements are not equal and are are ordered in a particular way, then they should be linearly ordered or totally ordered. Imagine as if they're like on a number line, if we were thinking, let's say, natural numbers. There was a very special event that happened in 2012, and colloquially is known as the Palo Alto TR. And it's a very, very lengthy paper. A bunch of folks concerned about C++ and its future, and specifically STL, including Alexander Stepanov, met and worked through all the STL types and all the STL algorithms and tried to catalog them and identify requirements and behaviors in the STL in a way that we can formally express that. And that's what that document does. That's way before C++20 concepts or ranges. So again, the salient bits. STL assumes equality is always defined, or at least an equivalence relation. I mentioned that sometimes we only mean equivalence, not total equality. STL algorithms assume regular data structures, and STL was written with regularity at its basis. And even if we ignore C++20 and C++ concepts, if we look at the Palo Alto TR paper, that should be fully obvious in the way that the intent on the design principles of the library are expressed there. And now we're getting to the main topic, regular and semi-regular types. Before we get to regular, we need to get to semi-regular. And by the definition in the yellow book here, semi-regular means default constructible, move constructible, copy constructible, and so on. In C++20 concepts, these are expressed in this manner. Same thing, replacing English words with mumbo-jumbo template and type traits. Same thing. If you look carefully, it's the very same thing. We just formalized what was in the Palo Alto TR. And regular just adds one more, but very important thing. And this is going to be the focus of the rest of the discussion, what equality means for types. And again, if we're using the language that we have since C++20, we can express this in a formal way using concepts. And we can see what equality is, at least in the way it's defined. But defining equality beyond the SEMA, beyond the syntax and the language boilerplate, truly defining equality is hard. And again, I'm going to quote from Stepanov's paper. Two objects are equal if their corresponding parts are equal, applied recursively, including remote parts, but not comparing their addresses, excluding inessential components, and excluding components which identify related objects. Sounds like hopeless task. Again, if we're defining simple value types, it should come natural through type composition. If we're using pointers and we're building all sorts of remote relationships in our types, then it becomes really hard. Related to equality, we have one more, let's say, simplification in the language, but it does come with some gotchas. So bringing consistent comparison operations. This really helps. The three-way comparison operators in C++20 really helps. It synthesizes a bunch of things, it introduces a bunch of categories of relationship strengths. It enforces symmetry in how we define operations, which wasn't the case before. So it's generally all good. But we need to understand a bit more. So as every new concept, pun intended, brings some clarity and some ergonomics to the language, it does come with some learning curve. So three-way comparison comes with relationship strength and categories to expressing that strength. So it can get complicated. I have a recommendation resource to get started on that. And yes, the spaceship operator will synthesize the common operations from that one operator. And inequality and equality finally are opposite things, because up until now we could pretty much define them to do weird things that are not symmetrical in any way. And of course, it comes with efficiency implications, because sometimes defining equality separate from the spaceship operator will yield performance benefits. So just lumping everything together in one operator, it's convenient, but it's not always the most efficient way. And there are many...
Can you elaborate?
Yeah, but not now. I can give you some examples. I gave a teaser at the bottom of the slide, but we can have a chat afterwards, because it's a lengthy discussion, and I'm going to run out of time for sure. So come to me and we'll discuss it. So a very good resource if you want to learn more about using the operator and some of the pitfalls and the subtleties In my opinion, this is the best presentation on the topic, so feel free to watch it if you want to learn more. And speaking of the operations, I couldn't resist. I just snapped this picture in this morning's keynote. Sometimes we just want a value. And when we're defining, even beyond CPP2, when we want a value type, we care about the ordering relationships, and Herb actually highlighted the exact thing that I cared about there. When defining values, ordering and how we establish ordering is very, very important. So before we get too far with C++20 and fancy futuristic stuff like CPP2, let's spend a few minutes on interesting C++17 types. For example, optional. I believe most of you should be comfortable with optional by now. Even if you don't get to use it, maybe comfortable with the concept and wishing you could be using it. So anytime you need to express a value or not a value, or possibly an answer or delayed in it. So this should be a common vocabulary type. This should become the norm in APIs and in the libraries you're using. And it's relevant to the ongoing discussion in that optional of T extends T ordering operations. Of course, an empty optional compares less than any optional that contains a T. And in most situations, you can use it as if it were a T. So it should be a foundational vocabulary type, and it will simplify code when used correctly. And it avoids a lot of error checking and branching when used appropriately again. And there are many more interesting ways to compose computational pipelines with C++20. But of course, we have optional of tref, and that comes with lots of discussions and contention in the community and the standards committee. I do recommend two resources for getting into optional of tref. Not coincidentally, they're written by the same author. One is an ISO paper, and one is a much lengthier blog post. The recommendation would be to allow rebinding to enforce shallow constantness but deep comparison. And the big debate here is about the rebinding, the optional reference. And this is, depending on who you ask, this is the best solution, of course. But it shouldn't be, definitely it's not a conservative solution. But it shouldn't be really a surprise. There are many implementations out there, including the one from Boost, but many others, which do support optional tref and, of course, the attached recommendations and rebinding behavior. And I couldn't resist having a talk without a crab. So I always say, if we don't know what we're doing, at least learn from others who've been doing it for a few years before us. So Rust has had option for many, many years, and it's throughout the standard library, and all crates are using it. It's a pervasive thing in Rust. The way it's used, it's uncontroversial and idiomatic. And if we can learn, maybe we should learn from people who have more experience with this. A very short video as a recommendation. I have a whole new presentation on the using optional and monadic extensions to optional and expected, about function composition and pipelines and continuations, and how you can chain computation without peeking inside, about mapping functions and all sorts of functional goodness. By the way, If you haven't seen Ben's presentation on applicative, that's another very valuable resource to have in your pocket. You can catch it on recording. I believe the version from C++ now is already online. Another interesting 17 vocabulary type is string view. And I think everyone should be familiar with string view. I don't need to make too much of an introduction here. The relevant bits to our discussion is that string view succeeds admirably at being a replacement for a constraint ref, for example, function parameters. Problem is that this is a new strange beast on the horizon. Up until now, we've had a very clear distinction between reference semantics and value types, and I've banged on value types for 40 minutes now. But this is a new kind of strange beast. It's not a reference type, it's not a value type. It's weird. It's sort of a borrowing kind of type. And it was our first such entity, but we have more now. They're basically references disguised as values. They lack ownership, they should be short-lived, they can generally do without an assignment operator. They usually appear in function parameter lists, generally not good to be stored in data structures or safely returned from functions. So again, going back to the operations that we define, string view is assignable, but assignment has shallow semantics. And the reason why that works is because strings are immutable. The underlying strings are immutable. Meanwhile, comparison, again, equality is the center stage of this discussion. Comparison has deep semantics. It actually does a lexicographic compare. So we see here, we see sort of a difference that we have shallow semantics for assignment, but deep semantics for comparison. But it sort of works because the underlying buffer is immutable. So it doesn't break the expectations of programmers, and we generally don't get any surprises. It does what we expect it to do. And as long as the underlying data buffer is extant, and because it's constant by how the type is defined, the usage sort of looks regular. It sort of satisfies the axioms and the expectations. And if we squint, it kind of looks regular. So when used properly, and that means mostly as a function parameter, string view works well, as if it's a regular type. But now we get to a new beast, a more recent addition. Again, not a value, not a reference. The weird kind of thing, the new thing, the borrow type. Think array view, and I think the biggest trap we have is that we've seen string view before. And we kind of think of span in the same way we think about string view. And that's a trap. Because as opposed to string view, the underlying data for span is mutable. And that's the whole point. We need to do something with those bytes, right? So span does not manage its storage. Lifetime is left up to the user. Same thing as string view. Nothing new there, except the mutability part. And that turns out to be very important. I'll skip the background. It comes from the core guidelines and GSL, but there we have a checked version, mind you. And now we get to the interesting bit. Does anyone know this C++ acronym? We love C++ acronyms. I love this crowd. You all get Stepanov books. No, I'm not Oprah. So the question is, should span be regular? Is span regular? And this is where you say, maybe I don't have enough experience with these kinds of concepts, these kinds of things. I'm sure there are smart people in the C++ committee that can figure this shit out. Well, no. we almost had a broken span. So what do we want here? Overloading operators can be dangerous when you change the common meaning of the operation. Let's try to establish some ground rules here. I said that before already. The meaning of copy construction and copy assignment is to copy the value of the object. I hope I was loud enough. The meaning of equality and less than is to compare the value of the object. Copy, assignment, equality are expected to go together as they do for built-in types. Again, going back to being intuitive to use. And when designing a class type, when possible, it should be regular, right? That's we always strive for. That's what the core guidelines say, and so on. So what should we do with span? Well, assignment copy is shallow. We're just dealing with the pointer and the size of the span. We don't expect assignment to actually copy the buffer. We could make comparison deep, as we do for string view, and just use standard equal or something similar to just traverse the buffer and have a deep comparison. However, as opposed to string view can't modify elements it points at. It's const, the underlying buffer is const. So shallow copy of string view is similar to sort of a copy on write optimization. You can think of it that way. But is span really a value? Do we really need a deep compare for span? When we write it as an operator, we might need to do that, but when we're being explicit, like using an algorithm like standard equal. But do we expect the operator to actually do a deep compare? The problem here is that span is trying really hard to act as a collection of elements over which it spans. We can do a range for over it. We can sort of pass it on to algorithms which expect ranges and usually work with collections. It's trying really hard to be to act like a collection, but it's not regular. And it basically has reference semantics that we already established. Also, deep equality implies deep constants or logical constants. That is extending the const protection to all the underlying parts. If we're going back to how we define whole part semantics in elements of programming. So all parts of the type that constitute its value should participate in equality and copy. That's what it means to define a proper type. Deep equality means the value of span and the elements it spans, not just pointer at size, which should be the shallow part. And if we want span to act like a lightweight representation of the element it references, we need to have a shallow comparator, just like we do for smart pointers. When we compare smart pointers, we don't actually dereference stuff underneath, right? And shallow const implies a shallow comparator. But a shallow comparator might be confusing to users, especially if they're using string view. We've established that string view has a comparator, and it's deep. It does lexicographic compare. So what can we do? We're sort of stuck. Like the thing we would be tempted to do, it breaks our intuition, and it's sort of inconsistent what we define for string view. So it's definitely confusing. So the only sane thing to do here would be to just not define equality. But that, and by the way, that's what it ended up in C++20. But it didn't start that way. Mind you, initially, it had a comparison function for equality. So it's a strange beast. Definitely not a regular type. users expect it to be a drop-in replacement for, let's say, a vector or array. And that happens to mostly be the case, unless you decide to copy or change its value. So it's semi-regular. I like this photo from Corentin. I think it's the best description for span. And by the way, there's a linked article there, a very good one, if you want to read it. So for non-owning reference types like string view or span, you need more contextual information when working with an instance of this type. Just looking at the usage, it's not enough. Local analysis is not enough. You need contextual information. That's why they're trickier. That's why there's sometimes there's traps there. And things you need to always consider when designing similar types or using these types. Is shallow copy? Does it do deep or shallow compare? Is it const? Is it mutable? Does it have an equality operator defined? What's the semantics of the equality operator defined? And so on. And they have reference semantics, although they look like value types. And yes, you can put them in containers. Don't do that. They have reference semantics, but they also don't come with the magic that makes references safer. For example, lifetime extension. Think of this really simple example, but you're going to run into examples which are much more complicated and subtle. And you are going to need tools to find those issues. And const string ref there extends the lifetime of the returned string from the name function, whereas the string view there does not. And it might just work. For example, if you're using a small enough string that fits in the SSO buffer of the standard string, it will just be there. It will just work. And you'll only discover it when you actually need to go to the heap, when you actually have a longer string. So for short strings, this might be a hidden bug. Speaking of lifetimes, I do recommend this presentation. It happened on Monday, but catch it on recording later. Lifetime Safety in C++ by my colleague Gabor Horvat. And by the way, our team here had a bunch of sessions this week, one more happening tomorrow. So I'm going to close up with a call to action. Make your types regular. I think I've been fairly obvious on that point. The best regular types are those that model built-ins most closely and have no dependent preconditions. Again, don't break the expectations. Don't break regular semantics. Let them be intuitive. Think of int, think of string, think of vector. They have to be in that vein. For non-owning reference types like string view or span or your own that you're defining in a similar fashion, you will always need contextual information when working with such an instance, and try to restrict those types to be semi-regular. Don't make them pretend there's something they're not. Don't disguise them as values. Don't break the expectations of your users, and try not to avoid to confuse them. And now I'm open for questions or complaints, of course. Don't throw things. I have a few time for questions on record, but I'm happy to chat on the hallway afterwards. Go.
Thanks. So a common temptation when you have like floating point back types is to define operator equals to represent approximate equality and take like float. Yeah, exactly. Exactly.
My face was revealing, right?
Yes, yeah, preaching to the choir. And like take floating point equality comparison in like ULPs and that. Now we can say concretely that makes the type not regular, where people would expect it to be regular. But do you have any examples of a concrete like consequence, something that like would be useful to convince people not to do this?
I wish I had. Floating point is an interesting beast, and it interacts weirdly even with standard algorithms in STL, because of NaN, of course, and because of how operations behave when you're adding, when you're floating point numbers, and they're strange beasts.
Yeah, because you mentioned earlier that they were associative, but
Yeah.
for floating point, not necessarily true.
No.
Yeah.
So it breaks many of the regularity assumptions. They're the necessary evil. Yeah. What can I tell you? Not the whole universe can be regular.
Nice talk, Victor. Simple question. Well, not a simple question. Do you think?
I'm scared now.
Do you think default construction should be part of regular? It seems to exist only to satisfy the axioms of regular.
Good one. I like how Ben said it was an easy one. Easy to state, difficult to answer. So if you ask Stepanov this, yes, default construction should be part of the discussion, should be part of the definition. In my experience, in many situations, you can get away without it. But I've seen many instances where I heard those words come out of Stepanov's mouth, like default constructible should be part of how we define regularity. Sorry? Yeah.
Yeah, thank you for the talk. To me, the problem with span and the string view seems like that, like initially we had pointers in the language with like shallow copy, assignment, and comparison, and everyone's used to that. And we have references with like deep assignment and deep comparison, right? And maybe it would be less confusing if instead of one span we had like array pointer, which exactly mimics pointer semantics, and array reference for reference semantics. And if you think about it, like span is effectively an array reference, but which tries to remove one indirection.
It is true. It's a convenience matter, I believe. It's so that it looks ergonomic when you just pass it around as function arguments, and it's just cheap to throw around and pass from function to function. And I think it's an ergonomics. It's a matter of, and I believe this was on the table before C++20. This was one of the discussions of the alternatives, to have two such types with clear meanings, or to rename span to have a clear name like span PTR or span ref or something like that in the vein, to be more clear in intent. That didn't happen, and in the fact that we ended up with just the one and how it behaves, I believe is just a matter of syntactical convenience. It was just a compromise solution. I think we've had similar discussions with other types, not just with span.
Okay, thank you.
In hindsight, it's hard to make a judgment call, but we need to deal with what we have.
So, similar question, but maybe just of intellectual curiosity. If we had given standard span, the same kind of interfaces, say, I don't know, optional, where you have to dereference it as if it's a pointery thing before you can get to what it points to, right? So in other words, standard span equality would be, is it the same address as the other thing? Star span equals star span. Does that solve part of the problem? Or does that just make it worse?
I wouldn't say necessarily makes it worse, but it's different because you no longer apply equality to that type.
Right.
When you dereference it, you're not,
Right.
that operator is not of, not
Right.
from
It
span.
isn't pretending to be a type anymore, right?
Yeah,
Gotcha.
you're using one level of indirection. You're just moving the concern to some other part of to the other type, to the underlying thing. So the same thing that we do for smart pointers, for example. So I wouldn't say it simplifies the problem, but it just moves it one level of indirection further. And it definitely wouldn't affect the operation of the type itself. Okay, we're over time, folks, but I'm happy to chat about these things on the hallway. Just catch me later.